Hi, I'm Chem's best friend. I make chemistry easy. I'm a graduate of MIT, and I have more than 17 years of experience teaching AP chemistry and chemistry classes. Please like and subscribe to my channel. And if you are interested in private tutoring lessons, the information is on the screen. Hello, are you ready to learn about titrations? I am. Let's go to my screen. So, here we have some pictures about titrations, but we want to learn why. Why would we do a titration? Well, let's say you go to a prep room and you need to have some acid or a base for your experiment, and you find right here this blue bottle. And this blue bottle says on it NaOH, sodium hydroxide. That's it. Well, what's the concentration of it? Is it how dangerous? How dangerous is it? So all this bottle says NaOH. And we want to know what is the concentration. So why do we do titrations? Why? To find the molarity of an acid or a base that somebody did not label. Okay, let's go over quickly some equipment that you might use. So first, you will probably pipette some acid into this guy. This is your Erlenmeyer flask. And this guy, this is a little, right here, we have our burette. Here is the bottom of this burette. You can see just the bottom of it right here. So the long, skinny thing is our burette. And I want you to notice something, that burettes have interesting way they are labeled. They have interesting way the tick marks are on them. The top is 0, and usually will go maybe to 25 mils, sometimes to 50 milliliters, but 0 is on top, and let's say 50 milliliters on the bottom. So watch out how you read the volume. So right here, the way to read the volume, we're going to go to the bottom of our meniscus, right? Bottom of our meniscus here. And we have, well, we know it's for sure between 21 and 21.5. Yes, I think this volume is 21.31. Remember our sig figs? Yes, remember our sig figs. So that's how we will read it. So you're reading it from the bottom down. Yes, and it's done on purpose because when you use usually a base in a burette, you're going to read your final volume minus initial volume, and it will give you a positive number that way. Otherwise, you'll be getting negative volumes. It will be kind of confusing. So it's actually done to make it easier. Okay, so we have our burettes, we have Erlenmeyer flasks, and let's think about what happens in a titration. So you want to find the molarity of an acid or a base, yes? Well, titration is a neutralization reaction, right? It's a double replacement acid-base reaction where we have, what do we have? We have our acid plus base makes water and salt. Do you remember that? Acid plus base makes water and salt. So every acid, here is our strong acid, HCl, that goes in contact with a base, the H plus and the OH minus will neutralize, yes, to form water. And so we have our H plus, OH minus right here, neutralized to form water. And then salt will be our spectator ions, will be swimming. So what we're going to do is we usually put our acid in the Erlenmeyer flask. We will know the volume of it. And then we will put base in a burette, and we will drop it drop by drop. drop by drop will go. So if we put a pH probe into our Erlenmeyer flask, it will look something like this. Now, this is a titration of a strong acid with a strong base. In another video, I will talk about weak acid and strong base, and then a weak base with a strong acid. So, but right now we're keeping it simple, strong acid with a strong base. So the pH will start off very, very low, and it will stay pretty low, and then it will increase. And then when we are halfway, I mean, we are kind of like, I'm going to say not halfway, we are done our titration, when all the acids is neutralized by all the base, where we just have water and salt, we're going to have neutral water, right? Neutral water, so pH will be 7. Now, if we keep going and just keep adding the base, that will be excess. We can keep going and increase the pH. So keep in mind, one acid, one HCl, plus one base will make water. How do you know when we are done? So usually our end point of titration is somewhere here. Let's call it here. Somewhere here will be our end point. Endpoint is your visual clue that you are just at or just past the equivalence point. And the visual clue will be an indicator. Indicator will give you. So based on what acid you're using and which one the titration you're setting up, you have all kinds of choices available to you of different titrations, in the different indicators. The one that's used more often in high school is right here, our phenolphthalein. So phenolphthalein is clear. It looks like water when it is with a neutral or acidic solution. And the moment it feels a little bit extra hydroxide, OH minus ions, it becomes pink. And usually we would want it like piglet pink. And that's how we know we are done. Now, the moment we are at equivalence point where our H plus equals OH minus, phenolphthalein will be clear. You will not see it. But when you are one drop over, you will see the difference. So your end point of a titration is very, very close to equivalence point here. So you're going to add the indicator. So, are you ready to see if you can solve a problem? Let's solve a titration problem. Let's say we have our hydrochloric acid and we know a concentration. So we have 0.10 molar hydrochloric acid and we have 25 milliliters. We use the pipette to take 25 mils of hydrochloric acid and we put it into Erlenmeyer flask. And then we had an unknown concentration of our base, sodium hydroxide. We didn't know it. And we started titrating. And then we took our initial volume and then final minus initial. And we realized it took us 19.5 milliliters to get piglet pink color. So now we took 19.5 milliliters to neutralize this acid. So let's solve it. So I think we need to realize that we're going to make neutralization reaction. So we're going to make H2O, water, plus salt, yes, and we need to realize that everything here is 1 to 1 to 1 to 1 ratio, which just makes it a little bit easier. 1 to 1 ratio. So that means in order to make this water, in order to neutralize it, I need to have my moles of acid. Let's write this down. My moles of acid have to equal moles of base. And I use that loosely, so let's make sure we really understand what I mean. In order to neutralize things, moles of H plus have to equal moles of OH minus. This is what we mean. This is important. Okay, let's keep going. Now remember, how do we get moles? I have volume, I have molarity. Do you remember that molarity was moles over liters? And that means moles have to equal molarity times liters. Yes, molarity times volume equals my moles. So, that's pretty great. So that means I can do, what can I do? I'm going to do my M1 V1 equals M2 V2. And now I can just plug in the numbers. Let's talk about acid. Acid will be my 1 and base sodium hydroxide will be 2. So do I have my molarity? Yes, 0.10 molar. Do I have my volume? Yes, 25 mils. And I am going to use mils here, and the reason is, you will quickly see why. So I do not know my molarity of my base, so my M2 I do not know. And if I use my volume, that it took 19.5 milliliters, look what happens. My M2, yes, my M2 has to equal, well, I have to do 0.10 molar times 25.0 milliliters over 19.5 milliliters, yes? And this is why I can use milliliters here, because milliliters cancel out, and I'm left with molarity. And I plug and chug, and I'm going to get 0.128 molar. So now I know my concentration of a base, which I used. And it has to make sense, right? If it's 1:1 mole to mole ratio, I'm using a little bit less volume. I'm using less volume than the volume I used of my acid. So that means the concentration, the molarity has to be stronger than 0.10, right? So, and it makes sense. I do have a little bit stronger concentration, higher concentration. Let's do something else. Let's use our acid and bases, and let's do a little bit of a stoichiometry problem. Let's do acid-base stoichiometry. Let's do this setup. We're going to have our nitric acid. It's a strong acid. We're going to mix it with some base. So I am not doing a titration here, because titration I stop when my moles of H plus equals moles of OH minus. Here, I'm just going to have a beaker of this acid, beaker of base. I'm going to mix them together. And my question is, what's the pH? What will be the resulting pH? Just to also show you, I can be anywhere on this curve. So normal titration, we go here and we stop here. Here is our end point. Here, I'm going to mix them somewhere on that curve right here. So we have to figure out lots of things. We have our stoichiometry problem. Let's do that. First, it's our double replacement acid base. So we will have water. We're going to have water and salt. Plus salt. And I'm going to follow my rules that I did in my double replacement reaction. So I first switch my cations. Okay. Now I have to look at my new compounds and I have to make sure that they are neutral. So H2O is good, but we have barium nitrate. Barium will be +2 charge. Nitrate will be my -1 charge. So I need 2 over here, yes? And now I can balance my reaction. Oh, I will need, let's make this, I will need 2. Yes, 2 of this. And I'm going to make then 2 waters. And I'm going to use 1 barium, 2 nitrates. And I look at my solubility rules, and nitrates are always AQ. And what the heck, let's also figure out how many grams of barium nitrate we can do. If we get rid of everything else and we put barium nitrate together, how much grams will that salt be? Okay, let's do, I think the easiest one to do right here is to do a rice table, a stoichiometry table. So let's go here. And just follow quickly the grid lines, and going to really fast fill this in. So stoichiometry table, I need to put MOL, moles, in here. So let's one more time write. I need to put moles, MOL needed. Moles go into my table. So I write my reaction, I write my initial, change, and the end, right? Just like stoichiometry problem, solution stoichiometry. And let's fill in whatever we have. Do you remember my moles also equal molarity times liters? Yes, molarity times volume. So if I can do this, here I have 0.250 molar and I have 0.1 liters. I'm going to have 0.0250 moles of my acid. And if I do the same thing with a base, I'm going to have 0.02925 moles of my base. Water, we don't care about, there's no concentration of water, right? And we will have at the beginning 0 salt. Now, keep in mind, I'm going to, there's 2-to-1 ratio. So for every 2 moles of my acid that I use up, I'm going to use 1 mole of base, and I will make 1 mole of my salt. I'm just using stoichiometry numbers. Okay, I need to figure out my limiting reactant. And hopefully you can see that for every hopefully you can quickly see it, that I will need, this is running out. Let's actually show this as a math quickly. Let's show this mathematically. So if I have, I'm going to start with, if I have 0.02925 moles of my base, I need 2 moles of acid, yes, stoichiometry, for every 1 mole of my barium hydroxide. And that means 0.0585 moles of HNO3 of nitric acid is, this is important, needed. Let's write it in red. Needed. I need 0.0585 moles, 0.05. Now let's look here. What do I have? Oh, wow, I have way less. So that means my acid is my limiting reactant. And by definition, limiting reactant will be all used up. So I'm going to use up 0.0250 moles. Yes? Now, this is 2x, yes? Because look at this. This number minus 2x, by definition of limiting reactant, has to be 0. It has to be. So if I do this quickly, just to show to you, 0.025 minus 2x equals 0, x has to equal 0.0125. Yes, this is what my x is. So I can go back to my table and say, aha, this is minus 0.0125 moles. And that means this is plus 0.0125 moles. Well, 0 plus this many moles is 0.0125 moles of barium nitrate. Yes? And this, if I plug this into a calculator, I'm going to get 0.01675 moles of barium hydroxide left over. Right? So let's answer how many grams of salt can I make? And then let's figure out our pH of a solution at the end. Well, let's go here. This is how many moles I have. Yes, this is how many moles of barium nitrate. And if I have this many moles of barium nitrate, I'm going to have, so how many grams of salt? So I'm going to have 0.0125 moles of barium nitrate. And you're going to look at your periodic table, get the molar mass. It will be 261.34 grams of barium nitrate per 1 mole. 1 mole of barium nitrate. You say, do I have to write this down? Actually, you do. And if we do that, we're going to get 3.27 grams of barium nitrate will be produced. Okay, let's figure out our pH. Remember, the question asked us about our pH. So let's do a little bit here. Okay, let's go here. What will determine pH of a substance, right? It either will be H plus ion concentration or OH minus hydroxide ion concentration. My H plus ion can come from an acid, but I used it all up. It was my limiting reactant. So that means I will still have some hydroxide ion. Oh, here it is. Hydroxide ion swimming. I have base left over. This base will determine my pH of a solution right here. This base left over. So let's figure out. Let's write down what we have. We have 0.01675 moles of barium hydroxide here. Now, this will split up, right? There is 1 mole of barium, 1675 moles of barium, but there is 2 hydroxide per 1 mole of a compound, right? So we will multiply by 2. So we have 0.0335 moles of hydroxide. You say, where am I getting this? Look right here, there is 2 hydroxides per 1 compound. So take this number, multiply by 2, and you get right here this number, 0.035 moles of hydroxide. And what is my definition of a concentration, right? Concentration of hydroxide is moles per liter. So what is my moles? What is my moles? I have 0.0335 moles of hydroxide in how many liters? Oh my goodness, let's go back. How many liters do I have? Let's go here. I had 100 milliliters in a beaker, and I mixed it with 65. So I have 165 milliliters in a beaker total, in my new beaker total. So this is 0.165 liters. And that equals 0.203 molarity. There you go. Now, if I take negative log of that, I am going to get POH. Do you remember that? So POH, because this is hydroxide, it's negative log of OH. And I can do that. So my POH is, take this number, 0.69. Now, what is the definition of pH? pH will be 14 minus POH, yes? So my pH will be 14 minus POH, which is 13.3. So here it is. So does this make sense? I hope it does. I think these problems are fun. And by doing a rice table, you can clearly see what goes away and what is appearing, what is disappearing. You can really clearly see it. So I hope you like it just as much as I do. And see you next time. Thanks for watching.